Hello everyone, Richard Walding here. I'm just going to run through some polarization demonstrations. In this case, it's just looking at some simple polarization that you do in grade 11 when you're studying light. Now in grade 12, we'll be considering the two components of electromagnetic radiation. There's the oscillating electric field E, which is the red one, and at right angles to that, and it's synchronized. It's the B field, the magnetic field, so it's oscillating as well, but you'll notice the two are in basically oscillating together. They're synchronized, so we can say that light is synchronized electric and magnetic fields oscillating together. The direction of propagation is shown by that little yellow arrow, and it's from left to right. So if you were standing somewhere on that black line, you'd notice as time went by that the electric field was oscillating. You'd feel it in one direction and then it'd go to nothing in the other direction. But of course, really all you'll see is just some light. So you'll see light going past you, or you're immersed in light such as the sunlight or the daylight. Okay, so that sort of diagram is more for year 12, but it just shows you the two oscillating fields. Now the one we're going to consider for year 11 is just the electric field, so we'll consider everything in terms of the electric field, and we'll see how we go. Okay, now light from the sun or from an incandescent bulb or something like that, let's consider the sun, is said to be unpolarized. Now you'll notice in that diagram on the left, the electric fields are shown in all different directions. Okay, so you'd have to think that in unpolarized light, the direction of the electric field can be any angle from 0 to 360 around that direction of propagation. So you think there's an infinite number of different ways it can, the angles that it can be at. Now I've only shown 3 there, the blue, red and yellowy coloured. So that's 3 electric field oscillations that you can see. Now in polarized light, we have selected one of those particular orientations. In this case it's the yellowy coloured one, and you'll notice we've drawn arrows at the bottom just showing that it's only oscillating in one direction. So all the others have been cut out, if you like. So the difference between unpolarized light and polarized light is the fact that polarized light only has oscillations of the electric field in one direction, or one plane if you like. Okay, now we can turn unpolarized light into polarized light by using a polarizing filter. Now the simplest thing that you've probably seen is just a pair of Polaroid sunglasses, or sunglasses that say they're polarizing or they've got a polarizing filter in them. Okay, now the simplest model we use is there's like a little picket fence, and you can see that grey fence, if you like, or grey gate has got slots in it running vertically. So that's a vertical polarizer. So the only orientation that it's letting through is the one in the vertical direction, up and down direction. The other planes are being blocked. Okay, so that's said to be a vertical polarizer, and the light that comes through is said to be polarized light. Okay, let's have a look at an example of this. Now, all I've done here is just take a bit of shiny plastic, stick it in the sun, and have a look at looking at it through some Polaroid filter, or a Polaroid filter. Okay, you can see it nice and shiny, reflecting the sun. And I'll bring up the filter, and you notice at certain angles it's really bright, and then it goes dark again because I've blocked out a lot of the polarizing angles have been blocked out. Okay, so that was nice and simple. Now have a look, just watch it. It starts off bright, and then as I rotate it, it starts off dark, and then as I rotate it, it goes bright. Okay, let's move on. Now, here's another example, just looking at some clouds through a window at school, and I've got two pieces of Polaroid filter. Now, they're oriented in the same direction, so you can imagine the direction of polarization is up and down or vertical. So when I put them one in front of the other, nothing much happens because the light just goes through the first one. It's polarized, so it'll have the light from the clouds will be only allowing the only plane of light that comes through will be the one in the vertical direction. Then it'll go through the first one like that, and then it'll come through the second one. But then watch what happens when I rotate the second one. Okay, here we go. So not much different. Now I rotate one of them, and you can see it's blocking out the light. So that's said to be crossing the polarizers. So I've got crossed polarizers there, and that blocks out all the light completely, or nearly completely. Okay, so let's have a look at a couple of, we've seen that. One of the other things we have to do in grade 11 is just mention that light can be modelled as a wave and as a particle. Now the particle model we usually do in grade 12 when we do quantum physics, but in grade 11 we just think of the wave model for light, and that's the one we're discussing. Now I'm using two pieces of grates out of the lab oven, and you'll notice the slots in the grates are parallel, so it's like having two polarizers with the polarization direction the same. Now I've got a student who's going to wave a bit of spring in the direction of the slots, and the wave will go through both. So if you watch, you'll see that. But now they're turning one, crossing it, and you'll notice the wave can't get through. So that's cross polarization. That tends to confirm that light is a wave rather than a particle. So polarization supports the idea of light as being a wave. Now I'll show you why it doesn't support it being a particle in a minute. But that's one aspect of light that can be demonstrated that it's modelled as a wave. Now the next one, this one, the student's going to drop a ball through there. Now the grates are parallel again, so the ball will go straight through. So imagine that to be a photon or a particle of light. It'll go through the polarizers, and watch this, straight through. Now they turn to cross them, and it still goes through. So if light was a particle in this particular demonstration, it'd just go through when you cross the polarizers. But we know it doesn't go through, so that tends to say it's a wave. It's better modelled as a wave. Okay, and lastly, let's have a look at a definition. Simple definition. We're talking about linear polarization. There is another type called circular. We're not going to worry about that, but it's a process in which the electric field, as I've mentioned, in light oscillates in a fixed plane perpendicular to the direction of propagation. So I've shown you that. And in contrast to an unpolarized wave that allows oscillations in all directions, but again they have to be perpendicular to the direction of propagation, but at any angle around that direction. Okay, so that's the definition, and we'll leave it there.